Hello, 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 everybody, and welcome back. Root Beer here with question number 24 on the 2007 Fermat paper. Let's jump in and take a look at our second last question. A line with slope 1 passes through point P on the negative x-axis, so that's this point P down here, and intersects the parabola y equals x squared at points Q here and R here as shown. Okay. So, since it's as shown, I'm going to say we can assume that Q also has a negative x value. I think that's reasonable. If PQ... Actually, no, Q has to have a negative R value. If P does, then going straight up, you're going to intersect this side of the parabola first. Anyway, if PQ equals QR, so these lengths here are the same, then the y-intercept of PR is closest to. So we want the y-intercept there. All right. So the information they've got, this line here is going to have to be unique, and it should depend only on the point P here. We know the slope. So if we just pick a point P on the negative x-axis, then we can say, well, gee, what are the two intersection points? And then talk about P to Q and Q to R. Yeah, I think that's fine observations for the start. We can redraw this picture here and see what we can see. Bring our parabola down here. Doesn't have to be super exact. It's our picture. We have P here. I'm going to say it's at negative P0. And yeah, it doesn't look like PQ and QR are the same, but that's okay. It's just a picture. Now, I suppose we could give names. Now, Q here has got to be on the negative x-axis, so I might say negative Q, and then this would be Q squared. And R over here is on the positive side, so we might say R and R squared. But I don't think we're going to be using all three variables for very long. Okay, so my line, since they give me the x-intercept, we'll use x-intercept form. The line is y equals mx minus a, where a is the x-intercept and m is the slope. So in this case, slope is 1. They tell us that. X minus negative p, well, it's just going to be x plus p. Y equals x plus p is our formula. So what can we say? Well, we can say a bunch of things. Q. How do we get Q? Well, Q has an x-axis, an x-coordinate of negative Q, but it's on the line, so the y-coordinate, Q squared, is equal to negative Q plus P. Alright, what about up here for R? R squared is equal to R plus P. Okay. So some helpful information there. What else could we talk about? We want the y-intercept, and that's 0, typically it's denoted b. But if I look at this this expression down here, y equals mx plus b, because our m was 1, we didn't have to do anything. Our b is equal to p. So we're just solving for p at this point. Okay. What else can we... Well, we haven't used the fact that PQ is equal to QR. So that might be useful. But hold on for a second, because I look at, say, equation 1 here and equation 2 here. And if I do 1 minus 2, that should be R squared minus Q squared is equal to R plus P. Let's get this observation out of the way. B is equal to P. We'll keep that over here for our own purposes. But R plus P minus negative Q plus P here But the p's are going to cancel each other out, and negative negative q is r plus q. Okay, but over on this side, this is a difference of squares. So r minus q, r plus q is equal to r plus q. So we have two possibilities. Either r and q add up to 0, or we can divide both sides and r minus q is equal to 1. I feel like now is when we should use the p to q is the same as q to r information. But how best to express that? Because we could say, well, pq is equal to qr, and there's a distance formula, and I think if we're really quick and we're not thinking this through, we might just say, let's plug it into the distance formula. And so I'm running out of space here, so let's just flip the page for a second. If I've got 2 points, x1, y1, and x2, y2, I can talk about their distance. Their distance is the square root of the difference in the x-coordinates squared plus the difference in the y-coordinates squared. So we take the big square root there. And you can prove this by setting up a very quick Pythagoras, rise over run, difference x and y's. But the point is, we might try and say, well, PQ, that's going to be this giant square root. And QR, well, that's just going to be this giant square root. We don't need that information. Okay? The slope is 1. So when we say, we'll just do a quick sketch again. Do a quick better sketch than that. So when we say we've got P to Q is the same as Q to R, we could do distance formulas, or we just say we've got the same right-angled triangle. And so the difference in the x-coordinates here has got to be the same, and the difference in the y-coordinates here has got to be the same. So we can say, well, since PQ is equal to QR, we get these equilateral, or not equilateral triangles, these congruent triangles. I know it doesn't look like that with our picture, but we can say that the two rises are equal. So from negative P to negative Q is the same as from negative Q to R. The run for both of these. And we can also say from 0 to Q squared is the same as from Q squared to R squared. Now we know Q squared and R squared a little better than this. But does this give us anything new? Well, the first one turns into Q minus P is equal to negative Q minus R. We could do 2Q is equal to P minus R. I guess that's some information. What else could we do? R squared is equal to 2Q squared. That's information. I don't know as this has particularly helped us. So maybe that wasn't the place to use PQ is equal to QR. I'm really liking this formula down here. Now it doesn't have any P's in it, and we want an expression for P, because remember we're looking for B, which happens to be equal to P. And P is just how many units over from the origin we have gone left to get to our point capital P. I think we should instead focus on this equation here. So, I didn't click over enough, did I? There we go. So we've got R minus Q, R plus Q is equal to R plus Q. So we have two options. R plus Q is equal to 0, or Dividing both sides by r plus q, we get r minus q is equal to 1. Now, I like this one, because then we get r equals q plus 1. I feel like this one shouldn't be true, but why? Oh, well, if this were true, r would be equal to negative q. And they'd be the same point, but r squared would be equal to q squared. And so the 1, which happens to be the slope of our line, which both of these points are on, you get r squared minus q squared over r minus negative q has got to be equal to 1. Okay, so r minus q has, so, that's impossible because then we get 0 on top and 0 on bottom. So obviously that can't happen, so we're looking at r minus q is equal to 1, so r is equal to q plus 1. Okay. So what have we got now? Well, here's p over here. We've got q here, and we've got r here. Again, this clearly is not appropriately scaled because these two do not look like they're similar in length. But what have we got here? Up at r, we now have q plus 1, and q squared plus 2q plus 1. And down here we have negative q and q squared. But now I know the height here. Okay, the difference between those two in height is 2q plus 1. So that means the difference in height here is 2q plus 1. And there we're using the fact that these are the same, these triangles here are congruent. So, but the height here is q squared, so q squared equals 2q plus 1. And that has got to only happen for a very, very small number of numbers. That doesn't get me p yet, but, we're on our way. We're on our way. So q squared is equal to 2q plus 1. When does that happen? Well, we bring it all over to one side. And I'm not seeing anything that's going to easily factor here. So we'll use the Pythagorean theorem. So negative b plus or minus square root of b squared minus 4ac all over 2a. So we'll get an 8 in here. So 2 plus or minus square root of 8 is 2 root 2 all over 2. We're looking at 1 plus or minus root 2. But q is assumed to be a positive value. That's why I said our capital Q is at negative q, because it's clearly on the left side of the x-axis. So since 1 minus root 2 is less than 0, we're going to go with q is equal to 1 plus root 2. Okay, now this still doesn't get us our formula, this still doesn't get us a value of p yet, but I think we have enough information here now. Well, let's redraw the picture, and there's got to be some way to get p at this point. Well, 2q plus 1 is here, but these guys are a slope of 1, so rise is equal to run. So, in fact, these have to have the same length. This is going to be an angle of 45 degrees in order to have a slope of 1. So this distance is also 2p plus 1, and we know this, 2q plus 1, and this distance over here is q. So p is equal to 2q plus 1 the horizontal distance between P and Q, plus Q, the horizontal distance between capital Q and the origin. So that's 3Q plus 1, but I know what Q is. It's 1 plus root 2. So we get 3 plus 3 root 2 plus 1, or 4 plus 3 root 2. So that's the actual distance. And now they said closest to, as I recall. Closest to, so we're going to get out our handy calculator. And 3 times root 2 is 4.24, and we add on the 4, we get 8.24, and that's going to be an answer of C. So C is our answer to question number 24. It did take us a little while, but we got it. And we didn't have to use any distance formulas. We just had to keep our wits about us. And then having the same slope there means that we get some nice congruent triangles, even though at no time at all when I was drawing my pictures did these two lengths look the same. But, as long as it's fine up here, it's a multiple choice contest. No one is looking at what you're writing. You don't have to write out any details if you can sort of just manipulate it all in your head. And your pictures don't have to be clear to anyone but you. Okay? Be as messy as you want, be as disorganized as you want, as long as you get the answer and get the right answer. Okay? So that's question number 24, all done away with. We've got just one more to go, question number 25. I will see you for that in the next video. Until then, take care.